Hello, students. We have not to go too fast, so now I want to do some example of a vector field, and then I want to calculate the equipotential surfaces, and I want to calculate some field line, and let you see from how to do that. That vector field, that is 2x divided by z. That's the first component. Second component, 2y divided by z. And the last component, minus x squared plus minus, and then the sum of x squared plus y squared divided by z squared. And I hope that you see that your z may not be equal to 0. So your z is not equal to 0, so you may not be in the xy plane. If you are busy with this vector field, I should say you are only busy if the z is positive or if the z is negative. In those regions you can work with it, but you cannot do something where the z is positive and can be negative or something like that. Then you have problems. You are going to that plane, z is 0, and there the vector field does not exist. So be careful. Now, most of the time there is asked if your vector field is conservative, and let me so f conservative, and that is a little bit not a stupid question, I should say. You have seen the last example where you see that the function the derivative satisfy the necessary condition, but it is not sufficient. So here also we look if they satisfy the necessary conditions, and if they satisfy the necessary conditions, we can also calculate the potential, but that will not directly say that your vector field is really conservative. Look to that last example, and with that last example, I mean what we have done in 3D, lecture 3D, and there your vector field is then equal to minus this term here. And you saw that they satisfy necessary conditions. The necessary conditions fulfilled, but f is not conservative. And if you like, you can also calculate some potential, and I think that will be the arctangent of y divided by x, x divided by y. And see that if your x is positive and your y goes from the upper part to 0, that you get your the value of the potential will go to the arctangent of infinity, and that will be pi divided by 2. But if your r is going from beneath to 0, so if your y is negative and you look to that value of your potential, you will see that it goes to minus pi divided by 2. Because the x divided by y becomes a minus negative, and that arctangent there is minus pi. And you see that they are not equal here. So be careful with that, conservative or not. and the necessary condition is fulfilled, but f is not. So, and here also with this example, what are we doing? We will look to the if the necessary conditions are fulfilled, we will calculate the potential, but you can still ask yourself if your f is conservative or not. All right, the necessary conditions. That has to do with all those derivatives. Now, and what do we know? What has to be done? The first component differentiated to y. And the first component, that is 2x divided by z, has to be equal to the second component differentiated to x. And the second component is 2y dz. And I can better do the following that I say from, if I calculate that derivative, I get a 0 out of it here, and that is equal to the derivative of the second component to x. So the first condition is fulfilled. So this is okay. Then we can do the second component, we can differentiate to the z variable. So this is the second component I say, and not the last component. So be careful. So the second component, that is 2y divided by z. If you differentiate to z, you get minus 2y divided by z squared out of it. And that would then has to be equal to the third component. And now you have this one here differentiated to y, and that is also, that is going well. So that is also true. So the first condition is fulfilled, second condition is fulfilled, and we have an in R3, so we have a third and that one will be that that is that the derivative to z of the first component, and if we calculate it, we get out of it minus 2x divided by z squared. That has to be equal to the last component differentiated to x, and I see also that that is true, and that is also true. So conditions are fulfilled, and we say then that f is conservative, but in mind always be careful. But we can now try to find a potential. And so we search a function phi that we will search, such that if we take the gradient of phi, that we get the vector field out of it. Now and then we have to solve a lot of certain kind of differential equations. The phi, if you differentiate to x, you will get out of it you have to get out of it the first component, and so you see that your phi, and then I let x and y and z I let away, so much writing, that you get out of it x squared divided by z, at both sides you integrate to x, and then we have, if you have just one variable, you should get a constant. If you but here we get out of it some constant, which some function which depends on only on y and z. If you now differentiate this phi, you get the first term of your vector field out of it. The derivative to x of the function g falls away. Now then, I calculate the partial derivative to y, and that gives you the partial derivative of g to y, and that has to be equal to the second component of your vector field. Now, and here we see that the g of that function, which depends on y and z, has to be equal to y squared divided by z, and then we get some function out of it which depends, and we have to add some function which only depends on z. Then we integrate it to y, and you should put a constant, but now we have only a z. So our phi becomes equal to x squared divided by z plus y squared divided by z plus some unknown function z. Now then we differentiate that mu function to the z variable, and we get out of it minus x squared plus y squared divided by z squared plus the derivative of h, and that one has to be equal to that third term of your vector field, and I see that the derivative of h to z is equal to 0, so that function h becomes some equal to some constant, and so we get for our potential we have x squared plus y squared divided by z plus some constants. Now, and often also the exercises there is given some point where the potential is given, and you see here that the potential 1, 1, 1 has to be equal to 3. Now, and then you fill in 1, 1, 1, and what do we have? We get 2 divided by 1 plus c, that has to be equal to 3. So our c becomes equal to 1, and we have our potential going through that point 1, 1 with that value which is given there. So we have x squared plus y squared divided by z plus 1. Here we have our potential. Now, the next question will be the equipotential surfaces. And now we forget that we have the potential is given in some point, so we are going to the general solution of our potential, that is this one here, x squared plus y squared divided by z is plus a constant. Now, equipotential surfaces, that means that your potential is equal to some constant, and that constant can is some real number, and you have to look for how those surfaces look. Now, and maybe we can in certain sense you can let that c away or something like that, that you say from okay, that you that we this c such as we can forget, so we have to make it as easier, and then we have the equipotential surfaces. This is the equation, and if we fill in that equation we get alpha plus y alpha squared plus x squared plus y squared divided by z has to be equal to alpha, and yeah, okay, and so we have alpha times z is equal to x squared plus y squared, and still, and that I have not written down here, but your z is still not equal to 0. That we are working in R3 without the xy plane. It is, and here you see your equipotential surface, and this one here is a parabolic surface. So you have, and your z is, if you can all, if you take your x0, you see z is y squared, so and you can rotate that around the z-axis. And so we have those surfaces here. You have that, maybe this one, and then you rotate around the z-axis. And I don't know this value of alpha, this, if that is negative. Oh no, it cannot be negative. Yeah, that can be negative also, but then also your z has to be negative. So here you have your alpha greater than 0, and here your alpha less than 0. If your alpha is less than 0, your z has to be less than 0, because x squared plus y squared is always positive. Okay. Now this is an equipotential surface that are parabolic surfaces, and then people can ask for an what it called a field line. Sorry. How to calculate that? This. Now, a field line, as it is, as already the name already says, it is some line, and that we define it by it has a certain so let we parameterize it by t, and then we have here our unknown coordinates of that line. T is a parameter, and if we are on that field line, the derivative of it has to be parallel to the vector field. So we are sitting on that field line. This is your xt, and then if you have some point here, you differentiate it, you get a certain sense, you can think to the velocity vector. Now, in that velocity vector has to be parallel to the vector field, and but I cannot, so I cannot write down is equal to the vector field, because then the length of those two vectors have to be the same, and I don't know if they are the same. So what to do then? Now put some function lambda t, and then multiply that vector fields. And this one here is a kind, this gives the difference between that derivative of the field line and the derivative and the derivative of the field line, so the velocity vector and the vector field vector, the difference. Now we can try to solve that equation. You get the x dt. So this is the equation we have to solve. And what do we have? The first component, or maybe I can better do here x, y, z, because the index is not so nice to work with. So we get here that the xdt term has then to become equal to some lambda t times, and then we have the 2x divided by z term, that is your vector field. And then we have here, in certain sense, our t. And what can we do with, and then let me write also all the other equations on the same way. So you get lambda t times, and I let this away, the t. We know they depend on t, and keep in mind 2y divided by z. And we have the last component, and that's also lambda t times, and then don't forget the minus sign, so minus x squared plus y squared divided by z. And let's see what we can do. To get that field line, keep in mind, field line, maybe we will not get directly a nice parameterization, but often you have the intersection of some surfaces. And so I am now searching those surfaces. So I am interested in those surfaces, and we are busy in R3. Now, if we have two surfaces and if they cut each other, then we know that that intersection, that is our field line. Now, let's see. What can we do? What can we do? That is now well, I see the following. This is equation 1, this is equation 2, and this is equation 3. We can do something with those equations, because I see if I multiply that first equation by dt, and if I multiply it in a certain sense with z divided by 2x, and the manipulations I am now doing, if you want to make them hard in mathematics, that is not easy, but okay, we do it here. What do we get out of it? We get z is 2x times dx is equal to, and then we get lambda t dt. That is out of the first equation. Now, at the same way, we can also manipulate the second equation, and we get also something for that lambda t dt, and that will be equal to z divided by 2y dy. So here we get some nice equation. What can we do? We see some z, those z's we can divide away, and then we can integrate those two equations. So I have the integral of 1, and I can also multiply everything by 2. I see, and if I should have done it well, this multiplication, the 2 falls already away, so I get z divided by x is equal to z divided by y. So my manipulations should already have given this equation. So I should have this equation if I integrate. And that means that the ln of the absolute value of y is equal to the ln of the absolute value of y of x is equal to the absolute L of y plus some constant. And if we take the exponential power on both sides, so if we take the exponential power of this one, that becomes equal to the exponential power of this one, and we see that the x becomes equal to some constant times y. And some people will say that the absolute value is equal to c times the absolute value of y. That is indeed, but if now your c may only be positive, otherwise it goes not well. But if you let your x and y free here, your c can be positive and negative. So we have the expression is okay. So your c is some element out of R, so it can be positive, it can be negative. Yeah, okay. And and realize that you have here some plane in R3. Because your Z is free. And we are busy in the R3, there we are solving that problem, and so there we are doing something. Now, now we can also combine. So what have we here done? We have taken the first and the second equation. What can we also do? We can also do the second equation with the third equation. And if we do that, so the second and the third equation, what do we get out of it? Then we get z divided by 2y dy. That is our lambda t dt, and that is equal to minus z squared divided by minus x squared plus y squared dz. And now I hope that you see that you have some problem here, because we have some dy, we have some dz, and we have some x in it. So that is not nice. So we have here to search for what to do then. What can we do there? And yes, but let's see. Look again here. What was our x depends on y. So if we fill in the that thing we have found before, our x depends on y. If we fill in that equation there, then everything will go well. No problem anymore. Now let's see. And what does it gives us? We and further on we have some z here and some z squared there, so we can divide out some z, and if we do that on a nice way, we get the following equation, that dy divided by 2y becomes equal to minus z divided by, and then fill in that x term, you get then cy squared, and so we have this here dz z. And now I have an equation only with y's and only with z's, and now I can try to manipulate it in such a way that I can uh, uh, integrate something. But then first I have to take the term with an y in it to the other side of that equation. And so what do we have? We get c squared plus 1 y divided by 2 becomes equal to minus z dz. Now, and then integrate everything. And what do we get here? C squared plus 1 times y squared has to be equal to, and then be careful with your 2. So maybe I'm here a little bit too fast. Um, you have to be. Um, let's see. Yeah, we have to divide by 4. If we differentiate this to y, you get 2y divided by 4. That is y divided by 2. Yeah, that is okay. And then here we have minus 1 over 2 z squared plus some constant. And that's okay. We have here. And now let's see what this gives to us. If we now put the y and the z to the other side, and maybe we can multiply everything by 4, that we have the fractions away, we get z squared plus 1 y squared plus 2 z squared is some constant. And what is this here? This is no x. X is of x is 3. We can better x 3. And so you have here a cylinder. Uh, along the x-axis. And that cylinder has is an elliptic form. And so those field lines are now the intersection of that cylinder. And then always give where is your x, where is your y, where is your z, and be careful with the orientation. Then we have that elliptic cylinder. It is not really a nice circle, but some elliptic one. And then you can shift that along the x-axis, parallel to the x-axis. That gives you that cylinder. And it is always a little bit. So we have here we have shifted it along the x-axis, so you have that cylinder, and also you can go to the end of it, no problem. And then you have also that plane. In that plane, that was some the z was free, but you are in the xy plane, so you have here your z is free. And then that cylinder and that plane will cut each other, and here you will have somewhere along the form of your field line. Okay, so those field lines, you have that cylinder, you have the, the plane x is sec y, and you have the cylinder c squared plus 1 times y squared plus 2 times z squared is some constant. So intersection of those surfaces. Okay, thank you.